Hello students, welcome back. In Local Extrema problems, I have only one problem left here, the trigonometric function problem. So let's copy and paste the shell from the previous problem set, and let's go from here. Okay, let's see. How about the graph? Not this graph, of course. I want to cosine of t plus cosine of t squared, and not x, but t is going from negative 2 pi to 2 pi. Okay, this is a periodic function, so I expected negative 2 pi to, let's go to 4 pi. Okay, all right. Looks like the same pattern is repeating. Local maximum, 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 minimum, minimum, minimum. They are infinitely many. Let's see. Let's go back to 2 pi again. So 0, 2 pi, negative 2 pi. So at 2 pi, apparently, we have local maximum. And by symmetry, this got to be pi, negative pi. So the conclusion is local maximum at any multiple of 2 pi to k pi. K is any integer. By the way, not x, theta. Theta is 2k plus 1 pi. So odd multiple of pi. So pi, 3 pi, 5 pi, and so on. Here 0, 2 pi, 4 pi, 6 pi, and so on. And to the negative the same. And then increasing, decreasing from pi to, okay, looks like increasing from odd pi to even pi, increasing. Now let's do decreasing first. So 2k pi, so k0 here, k1 here, so 0, 2 pi, 4 pi, 6 pi, and so on, to odd pi, 2k plus 1 pi, so next pi. So 0 to pi, 2 pi to 3 pi, or 4 pi to 5 pi, and so on. And then increasing from so 2k minus 1 pi to 2k pi. So negative pi to 0 pi, 1 pi to 2 pi, and so on. It's a bit hard to read, so let me put some space in between. Okay, if you have multiple parentheses, I have to make sure that it's easier to read. So that's what I can get from this graph, actually, without doing any calculation. Just observing the symmetry. Is this really right? Well, let's check. Take the derivative and set it equal to 0. Take the derivative, 2, and then cosine becomes negative sign. So negative sign. And then this is going to be actually a chain rule. You see, outer function is not cosine, it's the power function 2. So 2 comes out, and subtracting 1 from the power, and nothing changes inside, and then the derivative of the inside. That's a chain rule. Inside is cosine. And then derivative of cosine is negative sine. And setting this one equal to 0. Well, simplify this thing a little bit further. Negative 2 sine of theta. And then this is negative 2 sine of theta cosine of theta. Cosine to the first power, so just cosine. And then, looks like I can easily factor sine of theta out. Oops. Negative 2 sine of theta out. 1 plus cosine of theta equal to 0. So I'm going to get sine of theta is equal to 0. That's one possibility. Or cosine of theta equals negative 1. Yeah, either this is 0 or that's 0. Sine of theta is equal to 0. That's theta is, let's see, 2k pi. K belongs to any integer. And cosine of theta is negative 1. Theta is, let's see, cosine of 0 or 2 pi or 4 pi, those will give you positive 1. Cosine is negative, that means odd pi. Odd multiple of pi. 2k plus 1 pi. So even multiple of pi, or actually, excuse me, sine is 0, so any k pi as a matter of fact doesn't have to be even multiple. So this one actually absorbs everything. So all the multiples of pi and counterbalance with this graph here. Even multiple, we have maximums here. Odd multiples, we have minimums there, so they fit. So any multiple of pi, and this one is odd multiples only, but here even and also odd. So the conclusion, well, okay, it fits. Local maximum at even multiples of pi, local minimum at odd multiples of pi, decreasing from even to the next odd, increasing from odds to next even. Here's the graph. And then problem set and the solution and conclusion. Taking the derivative and setting it equal to 0 required a bit of a work, but well, considering that this is a trigonometric equation, we actually ended up with relatively simple trig equation as a matter of fact. There are a lot of terrible trig equations out there. Comparatively speaking, it's pretty good. We went through all those relative extrema problems I prepared here for this notebook, but just a little bit more, For only these two problems, let's consider intervals of concavity. and then find the x-coordinates of all inflection points. Let's do that. Let's consider those on top of those relative extrema, those local extrema, but I don't want the computations to get out of control. So let's do those only for first two problems, and for the rest, what should I do for the rest? Okay, let's remove the other problems, at least tentatively. Okay, all right. First problem. Here's a graph. So what do you anticipate? Concave down up to here, and then concave up here. So I expect an inflection point somewhere here. Just one inflection point. Do you see that? Concave down and concave up somewhere here. And then that's when the second derivative hits 0. You see, second derivative is negative, so that the first derivative is decreasing to have concave down. Now concave up, second derivative is positive, the derivative is increasing. You see, here's a summary version. You see, that's what I'm looking for. First derivative is increasing, second derivative is positive, first derivative is decreasing, second derivative negative. So we're going to go ahead with the second derivative. So the first derivative is here. How about the second derivative? Six x plus 2. Did I do this right? And that's 0. And that gives me x equals to 1/3, negative 1/3. Do you see that? Negative 6 seconds. So right here, negative 1/3, we have the inflection point. Negative 1/3. And then negative infinity, negative 1/3, concave down, concave up, and 1/3 to infinity. So concave down up to here and concave up from there. And you get it from second derivative equal to 0. All right? Go back here. First derivative changes from positive to negative when the second derivative, first derivative changes from increasing to decreasing. That's when the second derivative changes from positive to negative, or vice versa, and threshold when it hits 0. That's what you're looking for, and that's what you calculated here. Let's do some more of these.